We are now ready to start talking about section 3.2 in this Math 201 class. In the last section, we talked about how we can use the first derivative. So you start out with a function, and if you take the first derivative, which we can designate f prime of x, from the first derivative we learned how to determine the critical points of the function, and basically we did that by we took the first derivative and set it equal to 0, and we solved it. And once we did that, of course, critical points means your maximums, minimums, and what we call the neithers. We also learned that at this point, let me say this, we also sort of created the chart where we took our critical points and we made this chart, and then we were able to find the max or mins or neithers. And we also were able to determine when the function either increases or decreases. So for example, let me just, as a way of summary, here's why I'm doing this, because in this lesson we're going to talk about the second derivative. Now we've already talked about how to actually calculate and compute the second derivative, but in this lecture we're going to talk about the things we can learn from looking at the second derivative. And the way we approach the second derivative is the exact same way that we approach the first derivative. We go through the same steps. We end up learning different things, but the steps are the same. And that's what you're going to see. So the method we used to determine the first derivative and to learn this information about the function, we're going to do the same steps with the second derivative, and we're just going to learn different things. So that's what I want to try and highlight to you at first. So when we go through working with the second derivative, you realize we've done all this before, because it's actually the same steps we went through with the first derivative. So once again, the first derivative allows us to determine our critical points, and we use this chart. And also, first derivative can tell us where the function increases or decreases. And let me just draw a quick sketch of a graph and remind you of the kinds of stuff that the first derivative was able to tell us. Critical points for a function, first derivative, critical points are usually maxes and mins, sometimes neither. Of course, what happens to the first derivative at a max or a min? It's 0. And then when we look at this function, when the first derivative is positive, that means we have an increasing function. The first derivative goes to 0 at the maximum. Here we say the first derivative is negative, which means the function is decreasing. We can also think of this as like a negative slope. We get to the bottom here at the minimum where the function levels off. At that point, once again, the first derivative is 0. That's a critical point. And then notice the function goes back up, which means it increases. The first derivative becomes positive. So the first derivative helps us to find their critical points. Once we find their critical points, we can see what's going on in between the critical points, and that's how we learn that information. We are going to do the same thing for the second derivative. Matter of fact, let me draw the same graph and let me explain what the second derivative helps us to find. So if I draw a similar kind of looking graph, here's my function. Second derivative is all about, of course we designate it f double prime of x. When I look at the first derivative, sometimes I think of, really tells us where the function's increasing, decreasing. If I look at the second derivative, here's this new word. Second derivative is all about showing me where the, I spelled it wrong, concave up and also concave down. Sometimes you also say the concavity. Let me just explain this. When you're looking at a function and you're asked to determine where this function is the function or is the graph concave up, we're talking about the curvature, and concave up I think of like, think of a bowl. When we have concave down, I like to think of an umbrella. What do I mean? Let's look at this graph. If I look at this part, I'm looking at the curvature. This looks like an umbrella, right? If I were to look here, this is called concave down. This part of the graph is like an umbrella. When I keep going, I notice all of a sudden I get over here, and we call this concave up. I think of it like a bowl because it's sort of curving up. Concave down sort of curves down like an umbrella. Concave up curves up like a bowl. Now obviously, if I'm at concave down here and concave up over here, somewhere in between, it had to switch from concave down to concave up. So somewhere in here is like a transition. And it's not always obvious to tell. It's very subtle because you go here, you say, well, I'm concave down, I'm concave down. And then next thing you know, you say, oh, look I'm starting to be concave up. So in here somewhere, it switched. So for a graph, we just make our best guess and we say, well, maybe we'll say right there is the point at which the concavity changed. That point is called a point of inflection. Whenever the concavity changes, we call that a point of inflection. Now in the same way, the first derivative was able to tell us where the function increases and where it decreases. The second derivative tells us where the function is concave down and where it's concave up. And the whole idea is when the function is concave down, the second derivative is a positive number. Just like with the first derivative, a positive first derivative means the function is increasing. A positive second derivative says that part of the function is When the graph is, the function is concave down, that part of the graph has a second derivative that's negative. When it's concave up, the second derivative is going to be positive. Now here's a way I remember which is positive and negative, even though a minute ago I acted like I forgot. Concave up is like a bowl. You can also think of it as a smile, and a person who smiles is a positive person. So if I'm trying to remember concave up, is that second derivative positive or negative? I remember a smiling person is a positive person. A frowning person, a person who frowns is a negative person. So that's one way I remember concave up, concave down. Once again, for this function, at every value of x along this graph, if we were to look at the second derivative, it's going to be a negative number. Over here, every value of x I choose, and if I look at my second derivative along this function, the second derivative would always be positive. So what happens at the point of inflection? Well, common sense says if the second derivative is always negative in this first part of the graph, concave down, and it's always positive, concave up, at some point it has to switch from negative to positive. That switch happens at the point of inflection. So the point of inflection is where the second derivative is 0. So once again, let's compare. First derivative. First derivative is 0 at these critical points, and in this case it was maxes or mins and sometimes neither. Second derivative is 0 at the point of inflection. You notice the first derivative, these critical points, separates the function, the graph, from increasing and decreasing. In the same way, when the second derivative is 0 at this point of inflection, it separates the function into concave down and concave up. So that's why I said first derivative you could think of in terms of the big picture. First derivative helps us to figure out for a function or a graph where it's increasing and decreasing. Second derivative for a function or a graph tells us where the graph is concave up and concave down. So now what we're going to see is the same steps I followed to learn all the information from the first derivative is the same steps I'm going to follow with the second derivative. So now I go back to when I started. I said the first derivative, we take the first derivative, we set it equal to 0, we solve it, that gives us our critical points. Once you know the critical points, we can do our chart, and then we can determine where the function increases or decreases. We are now going to look at the second derivative. And the first thing we're going to do is determine the points of inflection. And how do we do that? We solve, or we set the second derivative equal to 0, just like we did the first derivative, except now we're setting the second derivative equal to 0. When we solve that, those are going to be the points of inflection. Then, based upon the points of inflection, we can create a chart, and then the chart is going to tell us for our function or our graph where it's concave up and where it's concave down. So what I'm going to do is I'm going to do some examples where we're specifically given a function and we're asked to find the points of inflection, and we're asked to determine where is the function concave up and concave down. So I'll do a couple of examples where we do all this second derivative work. And then eventually I'm going to do a problem where we take a function and we initially look at the first derivative and determine the critical points and the function increase and decrease, and then we turn around and keep going and dive into the second derivative and determine all this stuff. So in some problems we do both the first and second derivative and we figure out all these things. So now when you look at a graph, a lot of times these things are pretty easy to see. And what happens is sometimes when you have to do the math, it gets a little trickier. Just to make sure, let me talk a little bit more about concave up and concave down, just to make sure I'm just going to throw up a few graphs here, and we'll just do a quick analysis and visually determine where it's concave up, where it's concave down, and where the points of inflection should be. So how about if I do something like this? So once again, we're looking at concavity. We're looking at the places where this graph is like an umbrella and where it's like a bowl. And sometimes it's very subtle. Here, obviously, at the top here, that's obviously like an umbrella. So the second derivative here is negative. Once again, this is like a frown, a person frowning. Here, it's pretty obvious. This is like a bowl. It's like a smile. Second derivative is positive here. Here it's more subtle. When we start here, you can see it's a very slight curvature, but you can see it still is like curving down. This is like still concave down. So here, the second derivative would be 0, but then you notice very subtly, somewhere in here it changes, and this is a very slight curving up. So this is concave up. So this is where the second derivative is positive. So obviously, the concavity, the second derivative changed from negative to positive. Maybe the point of inflection is somewhere in here. Now here, the concavity is positive, but by the time you get to here, it's gone negative. So once again, anytime the concavity changes, there has to be a point of inflection in there somewhere. And the same thing here, the concavity is negative, concave down, and then concave up. So in here someplace, another point of inflection. Let me do just a couple more. It's good that you can visualize this, because in a minute, then we're going to do the math. So this one, how about if I do this? Let's just start. Concave up, positive second derivative. You get up here, all of a sudden, you're concave down. Second derivative is negative. So we had to transition into someplace, so point of inflection. In here, matter of fact, I'll stick a 0 here, because you know what happens at the point of inflection? The second derivative is 0. So these are all second derivatives. Second derivative is positive. Second derivative is 0. Second derivative is negative. Once again, very subtle, because next thing you know, we keep going. All of a sudden, we're concave up. We were concave down. We go concave up. And here had to be a point of inflection. And the last one, how about let's just go along. What's happening here? Concave down, second derivative is negative. I go along here. All of a sudden, I'm concave up. So in here someplace had to be a point of inflection. Concave up, but I get up here, all of a sudden I'm concave down. So my second derivative goes negative. In here someplace is my point of inflection. So I'm going concave down, but next thing I know, I get down here and I realize I'm concave up. Point of inflection. And then actually I get to here, concave up, and you can see it's starting to turn again to concave down, and there's a point of inflection. All right, so hopefully it's clear to you. Now what we're going to do now is, now we're going to be given a function as an equation, and mathematically we're going to start to find how to find the points of inflection of the function and the regions or the intervals of concave up and down. So once again, now you look at a graph and it's pretty easy to see the concavity. Although it's pretty tricky actually, if you're trying to very precisely determine the point of inflection, when you look at a graph, you don't really know. When you're looking at maxes or mins with a graph, we know exactly where the maxes and the mins are. But when you look at a graph, points of inflection, we know it's in here someplace, but where that thing shifts is very subtle. We're going to see mathematically we're able to determine precisely where the points of inflection are. Now the good thing is, like I've been saying, the way we go about looking at the second derivative is the same way we did the first derivative. So let me just quickly write down the steps we're going to follow to use the second derivative to find the points of inflection and where the function is concave up or down. So we're given a function as an equation. First thing we have to do is determine the first derivative. Now if the problem specifically says find the points of inflection, find the concave up or down, after we take the first derivative we immediately go find the second derivative. Now we're going to do a problem toward the end where we find the first derivative, then we spend some time with the first derivative and we go find the critical points and we go find the maxes and the mins. We go find where the function increases, decreases. Then we go find the second derivative and we learn all about second derivative. But for these first couple of problems, since we're really emphasizing the second derivative, we just take the first derivative and right away we just sort of jump and go get the second derivative. And then once we have the second derivative, we find the inflection points by solving. We take that second derivative and we set it equal to 0. The solutions for this equation will be your inflection points. And then once we have the inflection points, we can create a chart and determine where the function is concave up or concave down. These are really the same steps that we went through when we did the first derivative. All right, so let's do it. Let's jump in. Matter of fact, the problem I'm going to do now is actually one from the book. So from section 3.2, I'm going to work problem 6. And if I look at the actual instructions, let me read what the book says, because these are the kinds of problems you'll be doing in your homework. Let me flip to 3.2. All right, 3.2 for problem 6. It says, determine where the graph of the given function is concave upward and concave downward. Find the coordinates of all inflection points. So we're going to find the intervals where it's concave up or down, and then we have to find the inflection points. And here they want both the x and the y. So problem 6. Here's the function we're given. F of x equals x to the 4th minus 4x cubed plus 10x minus 9. First thing I do, take the first derivative. Here's the first step. Pretty straightforward. First derivative, right? 12x squared plus 10. Right away, since all I care about is the concavity and the points of inflection, I'm going to right away go calculate my second derivative. So I use the derivative rules again on my first derivative. So 12x squared minus 24x. So there's the second derivative. Now to find the points of inflection, you take the second derivative and you set it equal to 0 and you solve this equation. So here I'm going to factor. I can factor out a 12x. And then, pretty simple algebra, the solution to this equation, x is 0 or x is 2. There are my points of inflection. Once I have the points of inflection, now this tells me where in my function the concavity switches between concave up or concave down. So I'm going to do what I did with the first derivative and make a chart here, and I mark my points of inflection. And what's going to happen is these points of inflection are going to break my chart up into regions. Whoops. So here, I'm making a chart. Here are my points of inflection. In this case, I have 3 regions. Now what I'm going to do is, in each region, I'm going to choose a test point, choose a value of x in each of these regions. You can imagine this is like negative infinity and this is infinity. I'm going to choose a value of x. I'm going to plug it in to my second derivative, and then all I really care about will be, is it a positive or negative number? Because this whole region, the second derivative, does not change signs. Region 1, the whole region, the second derivative is always positive or always negative. At this point, I do not know which it is, but I know it's one or the other. So I'm going to go into region 1 and see if this is a positive or negative region. And then I'm going to choose a value of x in region 2 between 0 and 2 and determine for that region where the second derivative is positive or negative. And then I go to region 3. Once again, this is the same kind of thing we did with the first derivative, except now we're looking at the second derivative. So region 1, I'm going to choose x is like negative 1. So what do? I take my second derivative and I plug in negative 1 for x. So here's the equation for my second derivative. 12 negative 1 squared minus 24 times negative 1. Now I'm going to do this math, although I'm warning you now, as soon as I can tell whether it's positive or negative, I'll probably stop. I don't really care what the number is. I just care whether it's positive or negative. Negative 1 squared is 1, so this is 12 minus 24 times negative 1. You subtract the negative. You know what? The second derivative in region 1 is positive. And once again, I like to, as I learn this stuff, I go ahead and make a quick little sketch of what's going on. A positive second derivative, you know what that means? In here, my function or my graph is going to be concave up. That's what I've just determined. For region 2, I need to pick a value of x between 0 and 2. I'll choose 1. So I go plug in 1 for x in my second derivative equation. So 12 times 1 squared minus 24 times 1. 12 minus 24, right away I can see it's negative. Region 2 is a negative region. Region 2 means concave down. A negative second derivative means concave down. So in a sense, in region 2, my function of my graph is going to be concave down. And finally, region 3, I need to pick a value of x between 2 and infinity. I'll pick like 3. So I plug in 3 for x in my second derivative equation. So this is 9. 9 times 12, I believe, is 108. Minus 24 times 3 is, I think, 72. Looks like this is going to be a positive number. Region 3 is positive, and I'm concave up. So now we basically have figured out what's going on. It looks like it's concave up, then concave down, and concave up. If I were to make a very, very rough sketch of this, just to sort of visualize it, I could almost say, here's 0, here's 2. At 0, there's like some kind of transition. So maybe it's like this. And then at 2, it transitions again. It's a little tricky to see. So here's an inflection point. Here's an inflection point. Concave up, concave down, concave up. Now in this problem, they don't ask us to sketch it, but I just did that to sort of visualize it. But what they asked for were the points of inflection and the intervals where the function is concave up or down. So let's say, let's do the concave up. Where's concave up? Where is it positive? Regions 1 and regions 3. Region 1, x starts at negative infinity and it goes to 0. Region 3, x starts at 2 and goes to infinity. So these are the regions, the intervals, the values of x, where the function of the graph is concave up. And where is it concave down? In the second region, which is from 0 to 2. So there's the concave up, concave down. Now they asked for the points of inflection, but they asked for the coordinate, the x and the y. So I know earlier we determined the points of inflection to be 0 and 2. But since they want the coordinate, they want the x and the y, I've got 2 points here. I know the x for one is 0, the x other is 2. What's the y? I use the original function to find the y. You go back, way back to the original function, which is this here. Now this one's pretty easy. When I plug in 0 for x, this is 0, 0, 0. I'm left with negative 9. That was pretty simple. So I know one point of inflection is 0, negative 9. The second point of inflection, the x is 0, but what's the y going to be? Once again, y and f of x are the same thing. So in a sense, I could write this equation as y equals x to the 4th minus 4x cubed plus 10x minus 9. If I plug in 2 to the 4th minus 4 times 2 cubed plus 10 times 2 minus 9. 2 to the 4th, 4, 8, 16. 2, this is 8 times 4 minus 32 plus 20 minus 9. Looks like negative 16 plus 20 is 4. If I didn't mess up on the math. Sorry. You weren't seeing this when I was doing it. So I plugged in 2 into my original function. If I didn't mess up on the math, I think it's 2 negative 5. So here for the function, we've now determined where it's concave up and down and the points of inflection. Now I'm going to go ahead and do another example and then one more problem where I do everything. So let me stop this video now and I will continue on the next video.